In this video, we talk about the magic in a simulator. The simulator itself is a magician. Everything it does is actually should happen in a physical world, but we're making them happen in the virtual world. But magic should not be abused. So before we talk about when to use magic, let's clearly define magic. So we define magic as information that magically flows from one component to another component. For example, if we have a core here and we have a cache here, they typically have some control bus, address bus, or data bus so that they can communicate through these type of connections. And if in a simulator, we should let the data communicate through these explicitly defined buses, data channels, and we should not let them to go through these simulator defined message channels, saying if we want to ask the cache is busy, we can call a function called probably is busy of this cache module. So if this cache is busy, this information is magically flowed from the cache module to the core in this case. So why magic is bad? Because it introduces simulation inaccuracy. If we want to transfer some data from one place to another, we need to go through this data channel, and those bytes that transfers through these connections may create congestions and may delay other messages. And also it breaks down encapsulation. So if this core and this cache defines an explicit protocol that transmits messages through these buses or connections, then we also rely on an isBusy function that is defined in the core and the cache. So what if we want to replace this cache with a main memory module? What if this main memory module does not implement this isBusy function? Then we cannot really replace this cache with that DRAM, with that memory controller. So in this case, we're breaking down this carefully designed encapsulation so that we prevent ourselves from replacing this component from one component to another. So one example of how we support this no magic rule is that we support simulation with data. Typically, a simulator would implement the simulation in a way that the simulation is separate from the emulation process. In the simulation part, a core may send a request to L1 cache, and then this L1 cache send a request to an L2 cache, then this L2 cache may send a request to a DRAM, and this DRAM may return this message back to the core. And then in other simulators, a typical solution is that they simply calculate these messages, and then they only calculate the time that is required to send these messages, while the core can use a magic channel to directly access the storage that is stored in the DRAM system, so that it can guarantee correct emulation. In our simulation, we decide to use a combined simulation and emulation method. So for every channel that transfers this data from DRAM to L2 cache to L1 cache and to the core, we not only calculate the time that required to transfer these messages, we also carries the real data. So imagine this case, if you want to develop a cache coherency protocol. On the left side, you may calculate time in this L1 cache, L2 cache, calculate this message transfers for the coherency purposes. But if you have an error in this coherency protocol implementation, what you will see is that the timing model is not that accurate, but the emulation would still be correct. When you develop a new simulation model, when you develop a new design, typically you do not really have a real hardware to calibrate with. So in this case, we have to combine the emulation and the simulation process. And on the right side, if we develop this type of coherency protocol, and if this coherency protocol has error in it, we would see error in the final emulation result. Then the final emulation result typically has a ground truth so that we can compare and we know if we're implementing it correctly or not. So in this design, although it gives us lots of problems to debugging problems in L1 cache and L2 cache, but at least when we can get a correct result, correct emulation result, when after we run a simulation, we have the confidence that the current running system at least is modeling a feasible system. So we try to avoid using magic in GPU sim, but we cannot fully avoid using magic. And in what case we should use magic? So the rule is that one accurate timing model is not a goal of your simulation. For example, we support functional emulation. Functional emulation will report timing that is not accurate, but it is a general estimation. So in functional emulation, we only care about the emulation, the instruction emulation result to get a correct result, and we do not really care about timing model. And sometimes we want to do this headroom exploration. For example, we sometimes want to do we want to model a perfect prefetcher so that all the data is prefetched to a cache. In this case, we're definitely using some magic to move some data from the DRAM to the cache system. And we want to see what is the headroom of this design. So if this prefetching mechanism, even if the ideal prefetching mechanism, if it can only give you 3% of performance improvement, then probably it's not worth exploring this idea. But if it can give 2 times, 3 times headroom, then probably we want to design a more realistic system that tries to explore this headroom.